Hi, in this video, we will learn how to solve double integral in polar coordinate. In this example, the height function is given by 3x plus 4y squared, and you are going to find the volume under this non-rectangular region. Previously, you learned how to solve this by using the double integral with respect to the xy plane here. Therefore, we can take the double integral with respect to dx dy or dy dx. So if you choose integrate dy at outer, then your y limit must be constant. If you choose double integral dx at the outer integral, then the x limit must be constant. So you can substitute the height function inside this double integral and multiply with the area, then you obtain the volume. So this is the general formula for that. So you can see that this region is bounded by this equation which represents this curve, and the equation for this curve is given by this. From the equation of circle, we know that this is equal to the radius square. Therefore, the radius is minus 2 here and 2 here. So the radius here is equal to 1 and minus 1. In this example, you need 4 equations to find the volume under these 4 regions, where the first equation uses constant x limit from -2 to -1, which is here, and then the y limit is from 0 to square root 4 minus x squared, so which is 0 to this curve, where this curve you can find the y from this equation, which is equal to this answer. For the second region, we take the constant x limit from -1 to 0, which is here and here, and the y limit is from y equal to square root 1 minus x squared, which is this curve, and then y equal to square root 4 minus x squared, which is this curve. So you continue for the third equation, where you take the x limit equal to constant from 0 to 1, which is from here to here, and then your y limit is the same with the previous case, which represent to these two curves. Lastly, you take the x limit to be constant from 1 to 2, which is here. Then your y limit is from 0 to square root 4 minus x squared, which is these two curves. So if you compute the summation of all of these double integral, then you can obtain the volume within this region. In this example, since the geometry is symmetry, where you see the region 1 plus region 2 is equal to region 3 plus region 4, therefore instead of compute 4 double integral, you just need to compute the first 2 double integral in region 1 and region 2 and multiply the result by 2. So in this case, we use the dy dx approach. If you use the dx dy approach for the same problem here, you still need minimum 2 double integral to solve the problem. To simplify the calculation, in this case, double integral in polar coordinate can solve the problem by using just one equation. In addition to that, moreover, for a complicated shape like this, which is difficult to solve by using the normal Cartesian approach, the polar coordinate approach can solve this problem easily. We can convert the Cartesian coordinate into the polar coordinate by using these 3 equations. So for the Cartesian coordinate, previously the dA is equal to dx dy, or dA is equal to dy dx. For the Cartesian coordinate, we use xy to define the location. In the polar coordinate, we use the radius or the magnitude with the angle measured from the x-axis to quantify the same coordinate. So we know that the distance here is x and the distance here is y. From this triangle, we know that x is equal to rcos angle and y is equal to rsin angle. Therefore, you obtain these 2 equations. We can form a very small differential area here in the polar coordinate. where the dA is equal to the width here multiplied with the height here. So the height here is equal to dr and the width is equal to rd angle. So this can be found by knowing for a circle. So if you know the angle and you know the radius, to find the arc length here is equal to r angle. Therefore, for a very small angle here, you obtain the arc length here equal to rd angle. With that, you multiply it with the dr, give you the area. So this is your third equation. Let's solve the previous double integral using the polar coordinate approach. By using these three equations, we have the x equal to r cos angle, y equal to r sin angle, and dA is equal to r dr d angle. Let's find the limit for the angle. So you can see that for this case, the region is located at angle equal to 0. So if you continue in the angle direction, then this is the upper limit where the angle is equal to 180 degrees. With that, the lower and upper limit for the angle is equal to 0 and 180 degrees. And we know that 180 degrees is equal to pi radian. Let's continue to find the limit for the radius. And you should know the radius is located in this direction. From this figure, the lower limit for the radius is located here, where the radius is equal to 1. And the upper limit for the radius is this, where the radius is equal to 2, so that you obtain this curve. Therefore, the limit for the radius is from 1 to 2. With that, you success to obtain the region by using the double integral formula here. So you continue to multiply the r inside this formula to obtain this. And then you continue to integrate with respect to radius. So integrate 3r squared cos angle, make the 3 cos angle to be constant. Integrate r squared, give you r cubed divided by 3. So 3 can be cancelled, therefore you obtain r to the power of 3 cos angle. Integrate this term, you should make the 4 sine square angle constant, and r cubed become r to the power of 4 divided by 4. So the 4 here can be cancelled, therefore you obtain this. Substitute the r equal to 2 and minus with the 1 substitute with r equal to 1, then you can obtain this, and you continue to integrate with respect to angle. So 7 cos angle, after you integrate you obtain 7 sine angle. 15 divided by 2 is a constant, after you integrate it you obtain 15 angle divided by 2. So negative 15 cos 2 angle divided by 2, after you integrate you obtain 15 sine 2 angle divided by 2. So the bottom there, 2 multiplied 2, you obtain 4. So you substitute the upper and minus with the 1, substitute with 0, then you should obtain the final answer to be this. In this example, you have a 3D object where the density function is given. So from the shape you can obtain the volume, and when you take the triple integral of the density function with respect to the volume, then you are actually computing the mass of this object. In some problem, it's difficult to solve the triple integral using the Cartesian coordinate approach, where you let the dv equal to dx, dy, dz. In this case, you might consider to solve the triple integral by using the cylindrical coordinate, where the cylindrical coordinate is just the extension of the 2D polar coordinate that you learned before. Previously, in the polar coordinate, you have x equal to r sine angle, so this is the first equation, and then you have y equal to r cos angle, And also you have the differential area over here, where the area is equal to RD angle, which is the width here, multiplied with the ER. However, the polar coordinate is only applicable for 2D. To extend it to 3D, you need to include the Z direction. So in this case, the Z doesn't change, it still remains. So you need to include the dz here for this small element. And from here, to find the volume, you can take the previous area and multiply it with the Z. So this gives you the equation here. By using these four equations, then we can convert the Cartesian coordinate to the cylindrical coordinate. Let's try to solve this problem by using the cylindrical coordinate approach. We are going to find the mass of this object, where the density function is given by this. So you have k, where the k is unknown constant, multiplied with the square root of x squared plus y squared. So you can convert the x squared become r squared sine square angle by using this formula, and you can convert the y squared become r squared cos square angle by using this. So r squared here can be taken out, so that this can be cancelled. Sine square angle plus cos square angle give you 1 from the trigonometric identity, and you have the square root of the r squared. So these two can be cancelled, give you r only. Then you can multiply with the k to obtain kr here. So dv can be converted to the r dz dr d angle by using this formula. So let's find the limit for the z-axis. So you can see that this object is bounded by this hemisphere to the z equal to 4 here. So this lower z limit is given by 1 minus r squared, and upper z limit is given by z equal to 4. Then we continue to find the limit in the r direction. So this is the y-axis and this is the x-axis, and you can see that the radius is from 0 to the outer surface here, which is equal to 1. Therefore, the limit is from 0 to 1. 0 represents the center, and 1 represents to the outer surface here. We continue to find the limit for the angle. So the angle is equal to 0 at x-axis. So you can see that the object is rotated in 360 degrees. So this is the upper limit for the angle. And if you convert this to radian, you obtain 2 pi radian. With that, you obtain the angle from 0 radian to 2 pi radian. So let's integrate this part. Integrate kr squared with respect to z, you obtain kr squared z. And then you need to substitute the upper limit and lower limit, which is 4 and 1 minus r squared, inside the z. Then you should obtain this. 4 minus 1 give you 3. Negative r squared give you positive r squared. Then you multiply this with the r squared, give you 3r squared plus r to the power of 4. So you can further continue to integrate this component and lastly the outer component here to find the final answer. In this example, you see that we can use another alternative to solve this double integral, where you can see this double integral can be separated into the multiplication of these two single integrals. This can be done if your limit is constant here and your function is separable. For example, in this case, your function is this, therefore it can be separated into the r function separately and the angle function. So since the angle function is just 1 and your constant you can bring out. So you take the corresponding limit. So for the angle here, you have the angle function which is equal to 1, and then you integrate with the corresponding limit. And for the radius, you take the function for the radius here, then you integrate from 0 to 1. Right? So after you compute this, you should obtain the same result. And this gives the mass of this object that has this boundary.